Hey there, welcome back to Short Text 331. Today we're going to talk about the Fourier transform, and this is going to be part 1. So in this series of videos, we've talked about several different flavors of the Fourier transform. We talked about the Fourier series, we talked about the discrete Fourier transform, and today we're going to talk about the Fourier transform. And these are normally not really referred at as different flavors of the Fourier transform. That's just the way I like to see it, and I think it's useful. I think it's useful to think about all these transformations, all these objects as different flavors, different incarnations of the same idea. In the case of the Fourier series, we're dealing with a function defined in a finite continuous interval, and usually we say that this applies to functions that repeat themselves periodically, but that's just because that's what the Fourier series does. It's a series in terms of sines and cosines or a complex exponential, and those are periodic functions, and so of course they repeat themselves outside a finite continuous interval. Now here what we do is we take our function and we try to write it down as a series with coefficients determined by some integrals which come from an inner product, and the series that results will converge under certain conditions depending on the properties of your function. The result on the Fourier side, if you want, of the story is that we have a discrete set of coefficients which is typically infinite. So typically it's a discrete set of coefficients which we call AK, BK in the case of the Fourier series, or we call CK in the case of the Fourier series now written in complex exponential form. And those coefficients usually go all the way to infinity. They don't necessarily vanish except in special situations. So that's what we call, if you want, the Fourier side of the story. That's the result of doing the transform, if you want to think of this as a transform for the case of the series. Now, for the discrete Fourier transform, this is something that we saw in the context of linear algebra as a unitary transformation, as a special kind of unitary transformation. And here what we have is not a continuous interval, but we have a discrete interval, a discrete and finite interval. Usually we talk about endpoints. That's how I presented it in a previous video. And the result is a finite sum. So we do a finite sum, it always converges. There's no problem with that. And on the Fourier side, what you have is a finite set of discrete coefficients that when you assemble them, you recover your original vector, your original set of values defined on this discrete finite interval. In the same way that when you assemble this discrete set of coefficients in the form of your series, then you recover under certain conditions, you recover the original function that you had defined on your interval here, which we usually call f of x. Now, the Fourier transform, in a way, generalizes these two ideas. I like to think about it as generalizing this idea to the case where our function does not repeat itself outside this interval. So a case where this interval goes from minus infinity to infinity. So we're dealing now with functions defined on the whole real line. But you can also think about it as a generalization of this, where instead of having discrete set of points, you have a continuous set of points that go from minus infinity to infinity. And of course, you can also talk about a Fourier transform defined on this whole discretized form, but now going from minus infinity to infinity, so an infinite number of points. And I'm leaving that out of this discussion for now. In this case, what we have is an integral over the function. Here we do integrals to calculate the coefficients, and here we're going to be doing integrals to calculate a function, as you will see. And the integral converges under certain conditions, again, which we'll see in a future video. And the result of the transformation is that we have a conjugate variable, or rather a function of a conjugate variable k. So the discrete coefficients here that we called AK, BK, or CK, depending on the form of the transform, are discrete coefficients, and then depend on the variable k. Now here we have a function of the conjugate variable which will be continuous, and usually this variable represents a frequency or a wave number depending on the physics of the context. So let's dive right in then. So recall that we have the exponential form of the Fourier series, which we saw in a previous video, which takes this form. So we have our target function, and this is what we try to do. We try to represent it as a sum from k equals minus infinity to infinity of some coefficient ck times e to the ikx. So these are our Fourier modes, and these are our Fourier amplitudes, if you want. These amplitudes ck are calculated as 1 over 2 pi, the integral between minus pi and pi, of e to the minus ikx f of x dx. So this is, of course, for functions defined in the interval of minus pi pi. This can be generalized to functions going between minus L and L, or any finite interval that you want, really. This can be transformed and put into that whatever shape you want for a finite interval. Now, we're interested here in what happens if the function is not just defined in minus pi pi, and then and it doesn't repeat itself outside that interval minus pi pi, but actually has a whole profile that goes from minus infinity to infinity. So what happens when we want to extend this concept from minus pi to pi to minus infinity to infinity? And so in that case, instead of having a c sub k, we end up with a function that is usually denoted as f tilde of k, which is given by 1 over 2 pi, the integral between minus infinity to infinity now of f of x e to the minus kx dx. I'm going to call this equation 1. I'm going to use that later, but this is what we call the Fourier transform. So this function, f tilde of k, now a function of a continuous variable k, and k also goes from minus infinity to infinity, is what we call the Fourier transform of f. And we're yet to talk about what happens on this side. So this is the generalization of c sub k. So what about the generalization of what's on the left-hand side? Well, we'll see that in a minute. What we're doing here is that we're asking for an integral over this whole function, which may have some weird profile that's not necessarily periodic in any way, and goes from minus infinity to infinity, and will have some weird shape and peaks and valleys and so on. And so we're asked to do this integral from minus infinity to infinity together with this complex exponential factor. And what that accomplishes is that it analyzes our non-periodic signal, this weird shape, giving us its decomposition into Fourier modes. And so the reconstruction of f of x in terms of f tilde of k takes this form then. So this is the equivalent of our Fourier series. So this was our Fourier series. Now the equivalent of that, when we go from minus infinity to infinity, is an integral. It's an integral that has to cover all the possible values of k. So it goes from minus infinity to infinity, and we have our f tilde amplitudes here, and then e to the I kx dk. So we're integrating over k. So then we have a sum over all these amplitudes and the amplitude for each mode, e to the I kx. So these are then our Fourier modes, and so this is the representation we arrive at with the Fourier transform. This is what's called the inverse Fourier transform. So here we're reconstructing the function from its analysis. So if you want this, and in fact this is what I like to say, this is the analysis step. We analyze our function and we obtain the Fourier modes, the amplitude of each Fourier mode. So this is the Fourier transform, what I call equation 1, and what I call equation 2 here, here next over here, is the inverse Fourier transform. It's the synthesis side. So we have an analysis side and a synthesis side, and so this is what we obtain in terms instead of a Fourier series that we had in the discrete case or in the finite interval case. Now, recall that we saw in previous videos that this e to the ikx objects divided by square root of 2 pi, these modes are orthonormal basis. And we saw that in the context of the interval minus pi pi, or we might have seen it in the context of the interval minus LL. It's the same idea. And this is the equation that defines what we mean by an orthonormal basis in this context. So we have 1 over 2 pi, the integral between minus pi pi of e to the minus ikx and e to the iqx gives us the Kronecker delta of q and k. In other words, if q and k are the same, then we get 1. If they're different, we get 0. So these objects then are orthogonal to each other in that sense. And here we're assuming that k and q are integers, of course. Now, what happens when we want to generalize this, as we're doing, from minus pi to pi to minus infinity to infinity? Well, in that case, we are going to be doing an integral from minus infinity to infinity of the same modes in the same normalization, and what results from that is a Dirac delta. So this integral is actually 0 unless k is equal to q, and in which case you get essentially a singularity. You get an infinity, and the behavior of that singularity is such that you get precisely this Dirac delta of k minus q. And so this is the sense in which these modes that are involved in the Fourier transform now are orthogonal to each other. So we need, in fact, this orthogonality relation for consistency between equations 1 and 2. So let's go back and see what 1 and 2 were. So 1 is the way I define the Fourier transform. It's this integral. And 2 is the synthesis side. So how we write our original function in terms of the amplitudes that result from the Fourier transform. So what I'm going to show you next is that indeed, if you take the right-hand side of this equation, this right-hand side where we do this integral of f of x, and we insert in that this expression for f of x, then you obtain indeed that the result is f tilde of k. In other words, this formula is indeed the formula that you want for the amplitudes if what you want is a representation of your function in terms of this integral. Let me say that one more time. What I'm about to show you is that if you take this right hand side, then this expression in terms of an integral with 1 over 2 pi and f of x e to the minus I k x dx, this expression is indeed an expression for f tilde of k if what you want for f of x is a representation of this type, where f of x is given by an integral between minus infinity to infinity f tilde of k e to the I k x dk. So let's see how that works out. So we start then with the right hand side of equation number 1, which is given by this. So this is our integral, and we want to prove that that's indeed f tilde of q. So I'm going to use q here to not confuse variables k and q, because we're going to be doing an integral over k. So we have 1 over 2 pi, integral minus infinity to infinity, f of x e to the minus I q x dx. We insert equation 2 now in here, so this is part of our assumption. If f of x is given by this expression, by this integral, by this Fourier synthesis type representation, this is the inverse Fourier transform, then we obtain, I simply replace here f of x with this, and we obtain this expression here. And let me show you equation 2. This is our equation 2. I went ahead and simply inserted this form for f of x into my equation. So again, I replaced this f of x with this whole thing here in between square brackets. And I'm going to switch the order of the integrals. I'm going to pull this dk integral outside. Everything that depends on k here, only on k, is outside, and dx in. And so what I obtain then is the integral between minus infinity to infinity f tilde of k, now outside. And then in this square bracket, I pull in the 1 over 2 pi, the integral over dx, and then everything that depends on x. So e to the I kx is in here, e to the minus I qx is in here as well. I combine all that into this square bracket. This will be a function of k and a function of q, because I'm integrating over x, but I'm left with the with variables k and q that are free here. And then the dk at the very end, sandwiching everything that's inside the integral. And it turns out that this, by virtue of the orthonormality relation that I mentioned before, is simply the delta of k minus q. And so if this is the delta of k minus q, then we know how to do this integral. It's simply the function evaluated at k equals to q. And so that's the result, f tilde of q. So indeed, it turns out then, if we have this expression, this orthonormality relationship between the k mode and the q mode in the whole real line, minus infinity to infinity, giving us the Dirac delta of k minus q, then the inverse Fourier transform and the Fourier transform itself, or rather the opposite, this would be the Fourier transform and the inverse Fourier transform, which allows us to insert this expression for f of x, then all that allows us to give us consistency between 1 and 2. And indeed, this is the formula corresponding to f tilde of q. Now, all that is part of the formalities behind the Fourier transform. Let's see a couple of examples. So here is one of the most basic examples of the Fourier transform. Suppose that our function f of x is some constant a0 times e to the I k0 some mode, which I'm not saying what it is. It's, let's say some real number, k0, times x. So this is a function of x, and it's really just one Fourier mode, k0. That's what I'm inserting here. In other words, if my function f of x is given by this type of expression, I'm assuming that instead of being a whole sequence of modes, it's going to be just one Fourier mode alive, e to the I k0x. So that's what I'm saying here. Suppose my function is given by that. Then let's calculate its Fourier transform, f tilde of k. So that means we have to do this integral. But we know how to do that very easily, because if we insert f of x given by this form in here, then the a0 of course pops out of the integral. a0, 1 over 2 pi, integral between minus infinity to infinity of e to the minus I k minus k0 from here, x dx. And that of course is an expression for the delta. And so we have, as a result of assuming that this is my function and I do the Fourier transform, is that f tilde of k is just a constant a0 times delta of k minus k0. And so that tells me that my function f tilde of k is just the delta. So there's only one mode that survives, and that's how this is represented in Fourier space. So my Fourier transform of f of x is just the delta. It's 0 everywhere except when k is equal to k0. And so if I insert this, in other words, into my Fourier series, inverse Fourier transform representation shown here, then that is going to select, in fact, just that e to the I k0 mode, and of course it's going to return exactly what we started with, which is a0 e to the I k0x. So this is indeed exactly what we would expect. So f tilde of k then is just a0 times the delta. So interesting to note that this mode is basically, by Euler's formula, a cosine of k0x plus I sine of k0x. So this is a function that basically extends in x from minus infinity to infinity, oscillating up and down in the complex plane, and in all directions, and it doesn't die off. It doesn't die off on infinity. It goes like cosine k0x and I sine k0x. There's an amplitude a0, and it just keeps going up and down all the way to infinity. Whereas in Fourier space, it's very localized. It's just k0. It's just this stick here and 0 everywhere else. Now let's see what happens in the opposite case. What if we propose f of x to be just the delta? So now f of x is concentrated at a particular point in space times some amplitude b0. So it's completely concentrated at one point x0 with this amplitude or weight b0 if you want. And now we calculate its Fourier transform. What does f of x or f tilde of k, what does it look like? Well, let's do the integral. It's again very simple because we have the delta of x minus x0. It's very easy to integrate. So we go ahead and put this in here for f of x, and we go ahead and do this integral from minus infinity to infinity, f of x e to the minus ikx dx divided by 2 pi. And so when I insert that in here, I get b0 1 over 2 pi, and then the integral between minus infinity to infinity of delta of x minus x0 e to the minus ikx dx. And this is an integral that is trivial to do because it just tells me go ahead and with the integrand and replace wherever it says x, put x0. So remember that the Dirac delta is like a Kronecker delta, but now for integrals instead of for a sum. And we're covering all possible values of x. And so this simply gives us b0 over 2 pi, that's just along for the ride, and e to the minus ikx0. And so this now gives us the reverse of the situation we saw before. This is a function which is, you can plot it in the complex plane, is the cosine of kx0 minus I sine of kx0. And so as a function of k, it goes up and down from minus infinity to infinity. It just keeps going. For minus infinity to infinity in k, of course, is bounded by this. It goes up and down b0 over 2 pi and minus b0 over 2 pi. And so it basically oscillates like this. This is just a schematic. It's not a proper plot because this function is complex, of course. But the point is that this function does not die off at k very large. It just does not die off. You need all these modes to be assembled together in f tilde of k, and then you need all of them to contribute to this integral, so that in the end you get a delta of x minus x0. So let's review all this then. So if you have a function that's completely delocalized like this, and takes non-zero values basically in all values of x, and it keeps oscillating, and there's contributions from all the modes in x, but it's concentrated in k0, then you get concentration in k0 here in Fourier space. So it's just one mode in k0, and as a function of x, it goes up and down, and it takes on all values, or rather, it's generally non-vanishing for all values of x when x goes from minus infinity to infinity. Now here we have the opposite situation where the function is very concentrated around x0 and would completely concentrated, in fact, around x0. And what we obtain as a result for f tilde of k is the opposite of what we had before. It's now a function that basically is completely delocalized, and it's fixed in x0 here, but as a function of k, it takes on values that don't die off at k equals infinity or minus infinity or anywhere. So as long as k is real, of course. I'm assuming k is real and x is real. So this tells us something about the Fourier transform, which is very important, and it's a concept that is very deep and has big consequences for quantum mechanics, in fact. That is that when your function is very concentrated in x, like we see here, it's going to be very delocalized in k space. It's going to oscillate up and down, and it's not going to die off, or it's not going to die off very fast in k space as a function for f tilde as a function of k. If this function is sort of concentrated but not really, it's like a little mound around some value x0, then you'll see some behavior like that also in f of tilde of k, where it's not really going to extend to infinity, it's going to eventually die off. Now, the same is true on the other side. So if your initial function is completely delocalized in this way, it's given by a Fourier mode or a bunch of Fourier modes, and it doesn't die off at x going to plus minus infinity, then it's going to give you deltas like this in momentum space, in k space. Momentum space will be in quantum mechanics, so in k space. And so this is the root of the uncertainty relation between coordinate here played by x and momentum here played by k that you see in quantum mechanics. So if something is very delocalized in x space, it's highly localized in k space, and vice versa. If something is highly localized in x space, it's completely delocalized in k space. What's the compromise between the two? It turns out to be a Gaussian, and we will see next time that these two things reach that compromise when your function f of x is a Gaussian. It turns out that the Fourier transform of a Gaussian is also a Gaussian in k space, and their amplitudes, or rather their widths, are actually related. And we'll see then more precisely the mathematical origin of the uncertainty relation of quantum mechanics. So that's all I have for you today. I hope you enjoyed this video. I hope you found it instructive. If you did, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math, in English or in Spanish, you can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below. Also, as always, if you have any questions about these videos, or you have any interest in any particular topic, you can also leave a comment and let me know, or you can send me a message by email. And remember that the PDFs, all these PDFs are available. Just follow the link in the description. It will take you to my website, and then you'll find all the PDFs or all the videos. You can download them there. And that's all I have for you, and I will see you next time.